Electric forces obey something called the superposition principle, which means you can add forces together, one from each charge, to find the net force acting on a charge. So if you have more than one charge exerting a force, the first step is to always concentrate on the charge you want to know the force on, and then calculate the force from each of the other charge, and then add those force vectors together to get the net force acting on the charge of interest. So let's look at this example here. We have three charges, charge 1, charge 2, and charge 3. Charges 1 and 2 are negative, charge 3 is positive. So let's say we want to know the force acting on charge 3. We would first calculate the force because of charge 1 acting on charge 3, and we would calculate the force of 2 on 3. The direction would be towards each of these two charges because they're opposite to charge 3. And then finally, when we have these two force vectors from each of the charges individually, we just need to add those force vectors together to find the net force that acts on charge 3. So let's look at some example problems where we can calculate forces and see how to add force vectors. So in this first example, we have the fact that a bee can gain a charge from the air rushing over its wings and body as it flies. Suppose that a bee has picked up a charge of positive 103 picocoulombs. An avocado flower has pollen grains, each with a charge of minus 20 picocoulombs. How many electrons did the bee lose to gain this charge? And if the bee and flower are 2 millimeters apart, what is the magnitude of the attractive force between the bee and a pollen grain? And we have the additional fact that a picocoulomb is equivalent to 1 times 10 to the minus 12 coulombs. So first off, let's draw a picture of this situation. So we have a bee. So here is our bee, and the bee is flying and picks up a charge of positive 103 picocoulombs. And then we have a flower, and the flower has some pollen grains, and the pollen grains, so here's a single pollen grain, and the pollen grain has a charge of negative 20 picocoulombs. And in addition, we know that the bee and the pollen are a distance of 2 millimeters apart from each other. So the first thing we want to determine is how many electrons did the bee lose in flying to have accumulated 103 picocoulombs worth of charge. So we want to find the number of electrons that were lost. So we know that the charge, which I'll represent with Q for the bee, is, and this is the amount of charge that was lost. The amount of charge that was lost was, so this is Q that was lost. In order to gain 103 picocoulombs of positive charge, the bee had to lose 103 picocoulombs of charge. So that would be 103 times 10 to the minus 12 coulombs of charge was lost. Well, we can translate this into electrons because we know that each electron, so one electron, is equivalent to negative 1.6 times 10 to the minus 19 coulombs. And so that means that this amount of charge that was lost is going to be what was provided by 6.4 times 10 to the 8th electrons. So 6.4 times 10 to the 8 electrons were lost as the bee flew. So next we want to find the force, the amount of force, the magnitude of the force between the bee and a pollen grain. So the amount of force is going to be given by Coulomb's law, and Coulomb's law states that the amount of force is equal to Coulomb's constant times the amount of charge A, or in this case, the charge of the bee, since that's one of the objects, times the amount of charge of the other object, so this would be Q for the pollen grain, divided by the distance between the bee and the pollen grain squared. And you'll notice I'm using absolute value signs here. Whenever we plug numbers into Coulomb's law, they should always be positive. The reason being we find the direction based on whether the forces are attracting or repelling based on, do we have like charges or opposite charges. So we use the type of charge to find direction, and Coulomb's law is just used to find the amount of force. So if we plug numbers into Coulomb's law, the Coulomb constant is 8.99 times 10 to the 9 newtons meters squared over Coulomb squared. The amount of charge on the bee is 103 times 10 to the minus 12 coulombs, and then we multiply that by the amount of charge for the pollen, which is 20 times 10 to the minus 12 coulombs, and then divide the whole thing by the distance between the bee and the pollen, which is 2 millimeters, or 2 times 10 to the minus third meters, and then that gets squared. So the amount of force between the bee and the pollen is going to be equal to 4.63 times 10 to the minus 6 newtons. So that's the amount of attractive force between the bee and the pollen grain in the flower. So next, let's consider this problem. We want to know what is the force on charge A. So we can see that we have 3 charges, and both charge B and charge C will be exerting a force on charge A. So to solve this problem, first I'm going to draw a diagram showing the forces acting on charge A. So I have charge A, which is a negative charge, and then we have charges B, and we have charge C, and they form this equilateral triangle. And these charges B and C are both positive. So there's going to be a charge acting on A because of charge B. So the force of B on A will point in this direction. And then charge A will also be attracted to charge C. So this would be the force of C on A. So we need to find these two forces and then add them together to find the net force that acts on charge A. So first off, let's find the amounts of the forces. So the force of B on A is going to be equal to Coulomb's constant times the amount of charge A times the amount of charge B, and then divided by the distance between A and B squared. So if we put numbers in there, the Coulomb's constant is 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. The amount of charge A is 2 millicoulombs, so that's going to be 2 times 10 to the minus third coulombs. And the amount of charge B is also 2 times 10 to the minus third coulombs, so I'll just square that. And then the distance separating charge A from charge B is equal to D, which is 0.3 meters. So 0.3 meters squared. So the force of charge B acting on charge A is going to be equal to 4 times 10 to the 5th newtons. Okay, so then we also need to find the force of C acting on A. So that's going to be equal to KE times the amount of charge on A times the amount of charge on C, all divided by R squared. Now, if I look carefully and compare the numbers that I'm going to be plugging into this equation with the numbers that I plugged into this one, I can see that they're the same. Coulomb's constant's the same. QA is 2 millicoulombs, QB is 2 millicoulombs, R is 0.3 meters. So I'm going to get the same exact number for the force of C on A as I did for B on A. So this would also be 4 times 10 to the 5th newtons. All right, so now I have the amounts of the forces, and I'm ready to add them up. So I'm going to need to add these two vectors together. So that means I need to split them into x and y components. So if I redraw my diagram, I'm just going to draw these two forces that are acting at charge A here. So I have, first I am drawing the force of C on A, and then I also have the force of B on A. So those are the two force vectors I'm adding together. Now both of these force vectors make an angle of 30 degrees with respect to the negative y-axis. So the total angle here is 60 degrees according to the diagram on the slide. So this total angle is 60, so half of that would be 30. So this is 30. And this angle over here is also 30. So what I need to do now is split these vectors into x and y components. So let's start with the force of C on A. So this would be the x component, and this would be the y component. So if I first off look at the x component, it's opposite the 30-degree angle. So if I look at the sine of that 30-degree angle, that's going to be equal to the opposite, which is the x component, divided by the hypotenuse, which is the amount of the force vector. So that's F of C on A. So then the x component is going to be equal to the amount of force of C on A times the sine of 30 degrees. And so that's going to be equal to 4 times 10 to the 5th newtons. 4 times 10 to the 5th newtons times the sine of 30 degrees. And so that's going to be equal to 2 times 10 to the 5th newtons. Now, if I want to find the y component, I would use the cosine. The cosine of 30 degrees is going to be equal to that y component over the hypotenuse, the force of C on A. So that means the y component would be FCA cosine of 30 degrees, which is 4 times 10 to the 5th newtons times the cosine of 30, and that gives me an amount of 3.46 times 10 to the 5th newtons. Okay, so let's put some of these vector components into a chart for adding up the force vectors. So I have x, the x component, and the y component. And for FCA, the x component we found is 2 times 10 to the 5th newtons, and the y component is 3.46 times 10 to the 5th newtons. And I better put a negative because this vector is pointing in the minus y direction. The y component needs to be negative. All right, so now let's think about the force vector FBA. So FBA, if I draw a line over here, this would be the x component and this would be the y component. But if I look at this vector carefully, this angle here is 30 degrees. And the length of this vector we showed was the same as BA. So this hypotenuse is the same and this angle is the same. So this vector is going to have the same components. It's going to have the same x component. These triangles are identical, they're just flipped around. And so this x component will have the same magnitude as this one. The y component is the same between the two vectors. So I don't have to do any additional math to split this into components. I just have to pay attention to the signs when I write them down. So now let's look at FBA. So FBA has the same x component as FCA, it's just in the negative x direction. So this would be negative 2 times 10 to the 5th newtons. And the y components of both vectors are identical. So this is also negative 3.46 times 10 to the 5th newtons. So now if I add these two vectors together, the x components cancel, and for the y components I get a total y component of negative 6.9 times 10 to the 5th newtons. So that means the force on charge A, the net force would be 6.9 times 10 to the 5th newtons, and it's in the minus y direction. So the net force vector will be directly downward and have a magnitude that's twice the y component for each of these individual vectors. So it's all in the negative y direction, 6.9 times 10 to the 5th newtons.